So far in this course, we've dealt a lot with solids. So many of our chapters are dealing with substances. We've also recently covered liquids. So now we're going to talk about our third phase of matter, gases. So as a reminder, back from really the beginning of the semester, we talked about gases as being substances that do not have set volumes or shapes. So for example, if I have a solid, like let's take this pen here, my pen is going to stay about the same shape and about the same volume. On the other hand, if I have a liquid, I've got water, and I take it out of a pitcher and I pour it into a cup, when I do that, the water's going to stay the same volume. I'm not going to have a 2-liter bottle of water that I can pour and suddenly I get 10 liters. But it's going to change shape. And I'm kind of glad, right? It'd be weird if my gallon of milk came out gallon size shape, and I was like, oh, this doesn't work in my cereal very well. So it changes shapes. Gases, though, can actually change both. So for example, when you fill up a tire and you start putting air into it, the tire stays about the same size. If it's really flat, it'll grow a little bit, but once it gets up to its size, it's about the same size. You can put what would be perceived as a whole lot of volume into there, but it changes volume as you shove it in there. Now, as you get more molecules, that is going to change another property in the tire we're going to talk about in just a second, but it is not a set volume just because there's a certain number of molecules in it. So that's going to change. So to talk about gases, we need to actually talk about what's actually going to change in there is something we call pressure. So pressure is a term you have probably heard in the context of either tire pressure, of you're supposed to keep your tire so inflated and it's supposed to have so much pressure it can cause problems, you can get a flat, or if you have too much pressure it can cause it to explode or burst. Or you've heard pressure as it relates to weather, high and low pressure systems. So we need to define it here. What do we mean by pressure in this class? What we're going to mean is it's going to be the force exerted per unit area. So this is something that matters. So it changes with the area. So if I'm doing it over a large area versus a small area, this is different. So it's force exerted per unit area by gas molecules. So it's going to be by the molecules in the gas are going to be what's exerting the force. And it's going to be as they strike the surfaces around them. The surfaces around them. Now, we can also define this as an equation. To do that, we have that pressure is equal to force over an area. So for example, in our tire example, when one of the molecules in the air of the tire, they're moving around. They're going to collide with the surface of the tire. And when they do that, they apply a force, and they bounce off that, and they start going the other direction. So they apply a force on the tire when they do that. So different ways I can change that. One is our example we were just talking about. I can put more molecules in there. And it's about the same area. My tire doesn't suddenly grow to be huge, right? It stays about the same size. That's why it fits on my car. So as I add more molecules, well, there's more of them colliding with the surface. So my tire pressure goes up. This isn't the only way, though. For example, consider it, let's use our tire example again. If I'm going to fill my tire up, and it's a cold day outside, let's say it's about 25 Fahrenheit or something, it's below freezing, it's pretty cold, the molecules of my tire are going to move slower. They're going to collide with the surface less often. They're going to apply less force than if it were a really hot day where they were moving faster and they would collide more often and they would apply more force there. Therefore, I need to think about that. So practically speaking, what that means, if it's a really, really cold day, I don't want to fill my tire up quite as much because once it warms up, it might exceed the maximum force possible and cause my tire to rupture. So in that way, we have to think about this concept of how does pressure apply. So it could be the number of molecules in my tire increases the force, or the temperature outside can make it move faster. So we're going to talk about these different concepts that affect gases in a more technical sense a little bit. We'll give some terminology in a moment, and we'll show some equations to how, as a chemist, we can deal with these concepts that we hopefully have some type of conceptual connection to already. So to do this, we say we're going to talk about pressure. You've noticed in the previous chapters, one of the things we do is we come up with units for this, so we can talk at very specific amounts. So let's do that with pressure. So pressure is going to be measured in a couple of different units, and we're going to talk about them. So one of them, we write mmHg. This stands for millimeters of mercury. One of them is torr, and the third one we'll talk about is atm, or atmosphere. Which I could maybe spell atmosphere. I spelled atmosphere right, yay. So these are 3 units that we're going to use. So let's talk about where they come from. So millimeters of mercury comes from the way that we actually measure pressure. So the idea of a barometer was sort of the original designs. We don't use mercury much anymore, usually because mercury has some toxicity issues. But if we had a pool of mercury, and then we have a tube inside it, and inside that tube, we have a vacuum here. So there's no air in that part. What happens is the pressure from the outside air pushes on the mercury. And therefore, even though this is a narrow dish, the mercury will travel up this tube and it will be higher than the mercury around it. And the distance up it would travel is measured in millimeters of mercury. So how many millimeters did it go up? Or also you'll hear inches of mercury if you hear people using standard units instead of metric units. So that's the original way, that's how we get the term. Now you're much more likely to hear torr, which is just a different name for it. So torr and millimeters of mercury are the same unit. It's just that we're not worried about mercury specifically anymore, so it made sense to give it a different name. A lot of your barometers, we're not going to be using mercury here in most instances. Not no instances, there are some times where it still gets used, but it's less common. As a note, the reason we used it, just to mention, even though it's rather toxic, so we don't use it anymore, was because it's an incredibly dense liquid. I believe it's 13.6 times as dense as water, if I remember right. So it's like a liquid you could stand on. Like it's really, really thick. And I'll admit, it's kind of fun to play with, but it's dangerous, so we don't do that. I was a student at the tail end of that where people were still like, oh, it's okay to play with the mercury. Play with it on the table. It's fine. And they were like, oh, mercury vapors are probably really bad for you. And okay, maybe we shouldn't let undergrads play with mercury balls and potentially get it to absorb through their skin or something. That'd be bad. Or to breathe in vapors, it would be bad for them. So we don't do that. But it was a very dense liquid. So it was useful because it's really dense, it doesn't go as far up our barometer. Because if it's really dense, that means it's heavy. So it's harder to get it to move up. So it would take more force to do that, whereas if you had water in this barometer, because it's less dense, it would go further. It would take 13.6 times the distance. You'd have a super tall barometer that wouldn't fit and be practical. So there are other ways around that we do for barometers now. But designing one like this, it would have been more difficult to use it because water would want to go up further. Now, the other unit we use is called an ATM. So this stands for atmosphere. And this represents the idea that there are literally gas molecules on top of us all the time. And so an atmosphere is the standardized amount of what is the pressure at sea level on average that's on top of you for all those molecules that are up in the air. And so that was a nice thing. So we say 1 atmosphere is what that is. And that's a standardized amount we have now. And so obviously that changes with things like weather patterns. So it's a standardized amount that's about 1 ATM is pretty reasonable for what it's going to feel like from all the air molecules that are on top of you when you're at sea level. So these units can be converted between each other. So 1 millimeter of mercury equals 1 torr. This is a good thing to keep in mind because you will see both units sometimes. And then what we know is that 760 millimeters of mercury is an atmosphere. So this is how we convert between these two. And some things use different unit measurements. So you just have to be comfortable with converting. And since they're equal, that also means 760 torr is an atmosphere. So if you know one conversion, you know both. Now, we talked about the idea that these molecules are moving around and hitting surfaces. So I'm going to use a term to describe the theory of how we talk about these collisions. I'm not going to talk in a whole lot of detail, but I do want you to be familiar with the term. We call it kinetic molecular theory. So the idea behind kinetic molecular theory is that it's a simple model for the behavior of gas molecules. So what it means, we assume that when you model a gas, it's a collection of particles that are in constant motion. And those molecules are constantly moving. And so we assume constant motion, which is fairly reasonable for a gas. It basically always moves. It's got a temperature. It doesn't stay still. We also assume attraction between particles is negligible. Let's talk about what that means. Between particles is negligible. So what that means is that our molecules of gas, we're going to assume that we don't have to worry about two gas molecules getting really close to each other and going, hey, we like each other, we're attracted, or ooh, we don't like each other, we have the same charges, we're repelling each other. We're assuming those attractions are fairly negligible, which is a reasonable assumption. Some molecules you'll work with will start to become attracted to each other, and we have a different gas equation we'll talk about at the very end of this chapter that tries to adjust for that. But for the most part, this is a pretty good approximation, especially for a lot of measurements we're going to make in this course. What we also assume is that collisions are elastic. So what does that mean? So you'll probably talk about this concept a whole lot more in physics. But the general idea behind this means if two molecules hit each other, they work like billiard balls would. They would go boop and bounce right back off. And that means they would keep all of their momentum. While they may change direction, nothing's going to get absorbed anywhere. Whereas if you think of like if you had like a rock and then like something that was sticky that landed into it, they get stuck together instead. Now, some collisions could be a mixture of those. They don't have to be completely inelastic like they just stick. It could be like, oh, it hits. They stick a little bit, and then they move slower when they release. So we're assuming that we don't have any slowdown there, that there's no energy transfer in the collision that isn't just perfectly elastic. We expect them just to bounce like billiard balls would. The last thing we assume is... Where did my pen? My pen disappeared on my screen, although it didn't disappear on yours, I don't think. The last one is there's a lot of empty space. And this is compared to the size of the molecule. This is true for most of the gases you'll be working with in this lab. Now, I did talk about tires, and that's an example where this becomes less and less true as your tire pressure goes up. So as you add more molecules, you might imagine, as you get more, eventually they start taking up a more significant amount of your space. So this theory doesn't hold as well once there are a large number of molecules, and we have to worry about how much volume those molecules actually take up. But in many cases, you'll be working with samples where gases are really, really spread out. And that's true even for pretty condensed gases. So because they're so spread out, we can assume most of the container is empty space. There's only a little bit taken up by the molecules. And that's just going to be the assumptions we make that are affecting the equations that I'm going to be talking to you about. So what are the units we're going to use? So we've already defined pressure. And we talked about the units for it. So we'll represent that with a P. So that's our thing we're going to measure in atmospheres or torr or millimeters of mercury. Note there's also a unit pascals I'm not using in chemistry 1211 at least, but it is another unit of pressure, and I want to mention it in case you hear it brought up. So we're also going to worry about the volume of gases. So that'll be represented with V, and that's usually going to be something like liters we're going to use. We're not going to use standard units like gallons. We'll use stuff like liters or milliliters of a liquid. We're also going to worry some about the temperature of our gases. And as you might imagine, we're going to represent that with the letter T. And so temperature is usually going to be in Kelvin. So Kelvin is going to be an absolute temperature scale, where 0 Kelvin means there is no molecular movement. Remember, temperature is related to how fast molecules are moving. So higher temperature substances, like gases, if the gases get higher temperature, the molecules are moving around more. They have more energy, kinetic energy they're using through movement. So Kelvin is going to be the scale we use for that. It's linearly related to Celsius. So specifically, Kelvin, Kelvin is going to be equal to a temperature measurement in degrees Celsius plus 273.15. Or sometimes people will just add 273, depending on how accurate they feel they need to be. So it's a linear transition. This is different than Fahrenheit. Fahrenheit has a multiplicative factor as well, but we work so much in Celsius in this course and for everything else that we're not worried about trying to do Fahrenheit transitions. You can look that up or use that if you need to. But all of our thermometers and tools we have are going to report in Celsius or Kelvin, and this will let us go back and forth. So if you have in Kelvin, you subtract 273 or 273.15, you can get to Celsius as well. And then finally, the last thing we're going to worry about in this chapter is our number of gas molecules. So this is how many gas molecules there actually are. And so we'll use N to represent this. And so this is going to be measured in moles. So this is how it relates to all the previous materials we've been covering. You'll notice that each chapter that we've done towards the end of this first semester is about how many molecules we have, how to get to moles. So we had solids where we used molar mass to go from grams to moles. We just did molarity, where we took liquids that were certain concentrations so you could get between volume and moles. And now we're about to introduce in this next video how to get from moles of molecule from things like pressure. So chemistry focuses a lot on how many molecules do we have, because once you know that, we can use balanced chemical equations to figure out things like how many molecules we can make. So that's why we're so concerned with concepts like this. So this covers all the major terms we want to be able to use and the way we're going to measure them. The remaining videos, we're going to talk about the different relationships between gases, how we can figure out different values for pressures, volumes, temperatures, and moles based on information that we have, and then a little bit more how we can do some useful stuff with that.